I need to, ooh, that's too loud. I need to finish chapter 9 today. Yes. Our exam's going to be on chapter 8 and 9. I need to finish chapter 9, so I'll be asking for less questions today. So if you have questions, you can come and ask me after class. I really need to finish chapter 9. Otherwise, we're digging a really deep hole for ourselves when it comes to towards the end of class. So that's what I want to do today. We're going to get started. Everybody knows we have a midterm on Friday, yes? All right. So we left off last time talking about making tosylates in order to turn an alcohol into a good leaving group. Once you make a tosylate, then you can react it with any of the nucleophiles we talked about in chapter 7. So examples of common good nucleophiles would be N3 minus, cyanide, iodide, bromide, HS minus. All right, so why is the sulfonate anion such a good leaving group? Good leaving groups are weak bases, right? Good leaving groups are weak bases. pKa of the conjugate acid, what's the conjugate acid? Tosic acid. TSOH, we talked about that at the beginning of this chapter, is minus 2.8. All right, so we know it's a good leaving group, and one of the reasons why it's a good leaving group is it is highly resonance stabilized. So I have all of the resonance structures drawn here, and so it's resonance stabilized. And we also have the negative charge delocalized over 3 atoms. All right, so we can make a tosylate. We can treat it with any of the nucleophiles that we talked about in chapter 7. The other thing we can do is we can treat it with one of the halogens, and we can make an alkyl halide that way in a 2-step process. So this is what it would look like. I'm going to just draw this 5-membered ring on its side. That's looking really ugly there, but you got the idea. Okay, and then remember when we make a tosylate, we have retention of configuration. So we have our hydroxyl up, that means our tosylate is up. So we're going to write OTOS to abbreviate that. And then when we do sodium bromide, that's going to be an SN2, therefore inversion. And when we do that, we get overall inversion of configuration. So we can make alkyl halides this way via tosylates. Just another reaction to put in our arsenal here of reactions. We're going to actually start cataloging reactions in chapter 10. We're not going to do it yet, but we will need to do it starting in chapter 10. We'll talk about that when the time comes. All right, so let's summarize. Alcohols can be converted into alkyl halides with HBr, HCl, HI, or thionyl-chloride pyridine, or PBr3 pyridine. In addition, an alcohol can be converted into a tosylate, then treated with bromide, chloride, or iodide to convert it into an alkyl halide. We have a lot of different methods here, and these methods are complementary, so it's important that we have more than one. Once you have an alkyl halide or tosylate, you can do all of the substitution and elimination reactions seen in chapters 7 and 8. So we really aren't limited to halides. We can actually have tosylates, and we can do eliminations from chapter 8. We can do substitutions from chapter 7. Here's what you can't do, what a lot of people try to do on the test, which will not work. A lot of people say, well, why do I have to memorize all of these ways of converting an alcohol into an alkyl halide or a tosylate? Why didn't I just treat it with acid? Protonate the alcohol, make it a good leaving group. So this is what some people try to do. And we're going to draw what you're thinking, and then we're going to say why that doesn't work. So if you're feeling very clever about this idea, I don't have to memorize all this stuff. I can just use this. And so let me draw the product. It seems reasonable. This would be the idea here. And, but that actually doesn't work, so we're going to put a big X through that. A green X through that, yeah. Okay, this is what's going to happen instead. Here's our N3 minus. It's going to deprotonate. So what you end up getting instead is your alcohol back again. Oops, didn't want that. And then HN3, hydrozoic acid. That's what you'll end up getting. So why doesn't that work? Why does that work with HBr? The reason that that works with HBr is because when you protonate the alcohol with HBr, you're left with bromide ion, which is an extremely weak base. And it's also a really good nucleophile. So the bromide comes in and does backside attack and kicks off water. N3 minus is not an extremely weak base. The pKa of the conjugate acid is 4.3. So it's just too strong of a base to do what we want it to do, which is substitution, when the fastest of all reactions are acid-base reactions. And so that's why that doesn't work. So make sure you don't try this strategy. There's also a sapling problem that asks the same question. And so take note of that. I've put that on tests before because it's a really common mistake that students make. All right, so the last thing we want to talk about in this chapter is ethers. We're going to talk about regular ethers, and then we're going to talk about epoxides. So there's two mechanisms for epoxides that could potentially be on the test, and I typically ask both of them. There's an acid-catalyzed reaction, and then there's a base-catalyzed, and I typically ask both of them because those are reactions that prepare you well for reactions that are coming up. And so that's why I do that. All right, so ethers, like hydrocarbons, are remarkably inert to most chemical reactions. This is why they make such good solvents. So here's some common solvents. You've probably used diethyl ether in lab already, haven't you? Yes? Tetrahydrofuran is another one we'll see a lot in chapter 10. Tetrahydropyran, not as frequently, and 1,4-dioxane, you might have heard of that. We're not going to use that too much. We mostly are going to use diethyl ether. But the thing that we like about a solvent is we don't want the solvent to react with our compounds. So these are really very, very stable compounds. Ethers are, however, cleaved when heated with hot, concentrated HI or HBr. These are the only ones that I'm going to use here. All right, and so let me give you an example here. If we take this ether, terp-butyl on one side, terp-butyl methyl ether, and we treat it with HI, one equivalent of hydroiodic acid. So when I say one equivalent, I mean a 1-to-1 ratio between the HI and the ether. And if we do that, we get two products. We cleave the ether, we break it into two pieces. We get, if we use one equivalent of HI, we get an iodide and an alcohol. If we continue to react it, if we add a second equivalent of hydroiodic acid, this alcohol that we just made is converted into methyl iodide. Originally, the first form product will stay exactly the same, so we'll still get this, but the alcohol will be converted into an iodide. So we'll end up getting two things, that plus that. All right, let's look at the mechanism, and then we'll talk about how we figure out, if we just use one equivalent, how do we figure out which one is the iodide and which one is the alcohol? So we're going to do a stepwise method for figuring that out. First, let me give you the mechanism. The first step is protonation. I mean, already you're starting to see that protonation, what we learned, the mechanism we learned back in chapter 2 is used so frequently. We use it over and over again, and we will continue to do that throughout the whole year of organic chemistry. So arrow comes from the lone pair on oxygen. We grab the hydrogen. we break the hydrogen iodine bond. All right, so what this is looking very similar to is when we protonate an alcohol, right? So if this methyl on the right-hand side here was a hydrogen, that looks exactly like when we protonate an alcohol. So the only difference is that now we have a methyl there instead. The second step is going to be, and we've seen this over and over again in this chapter, SN1 or SN2 depending on the substrate. So that's the decision we're going to have to make. So these are the two considerations here. How we decide. If departure of a leaving group gives a secondary or tertiary carbocation or a resonance stabilized carbocation, then a secondary or tertiary carbocation or a resonance stabilized carbocation will form first. That's what you have to remember. Okay, so if we can make a secondary, a tertiary, or one of those resonance stabilized carbocations, that's the first thing that's going to happen. And therefore, if we form a carbocation first, then that means it's an SN1. SN1 will be the fastest. Second consideration, if we don't have that, if we can't form a secondary or tertiary or stabilized carbocation, if we form an unstable carbocation like a methyl, vinyl, aryl, or unstabilized primary, then a carbocation will not form. The halide ion will attack the least hindered side. So therefore, SN2 will be the fastest. All right, so let's look on the next page and see if we can do this. All right, so I'm going to go through this process with this substrate here. Isopropyl on the left-hand side, ethyl on the right. Let's go through the process. First step, HBr, we protonate. You will only see this with hydrobromic acid and hydroiodic acid because these are extremely, extremely strong acids. All right. What was that? What? HI. Oh, it's HI. Okay. Well, yeah. Let's fix that. I don't know why I said HBr. I always use HI anyway. Okay. Okay, so here's our decision-making point. First step is easy. We protonate the oxygen. And that's what we're doing is we're actually making it a better leaving group. All right, so it looks like on the left-hand side we have an isopropyl group. And so if we break that carbon-oxygen bond, we can form a secondary carbocation. That's going to be fastest. We can form a secondary carbocation. So then what's going to happen is this group is going to leave. Boom, just like that. That leaves us with an isopropyl carbocation, secondary carbocation. We always have to be alerted when we make a carbocation for rearrangements. Can that rearrange to anything? No. So we don't have to worry about it in this case. We get that plus the other side is ethanol. So I'll just draw that. And then what's going to happen next? The iodide that we just made. This is pretty much an extension of the HI reaction we talked about towards the beginning of this chapter. The iodide is going to come in and attack the carbocation. And then we get, we'll go here, CH3, isopropyl iodide, plus ethanol. See how we figured out which one is the alcohol and which one's the iodide? By reasoning our way through the mechanism, following the two guidelines. With the second equivalent of HI, the ethanol can now be converted in just like we did at the beginning of the chapter. Let's go through that one more time. That's a good review for us. HI, this is primary, so we know it's going to be an SN2. So you should know this mechanism like the back of your hand, right? Because that's a possible mechanism for this upcoming midterm. Okay. Just like that, and iodide being such a weak base is not going to want to deprotonate again. What it's going to want to do instead is do backside attack and kick off water. So that's how we get converted into the iodide. So if you use excess or two equivalents, you're going to get everything converted to an iodide that can be converted to an iodide. Here's a second example here. Example 2. We have methyl and ethyl on each side. Let's go through the process again. Can we form a secondary, tertiary, or resonance stabilized carbocation? No. That means we're going to do an SN2. Okay, so let's draw our protonated ether. Okay, so no good carbocation. No good carbocation. Therefore, we're going to get an SN2. Which side is the iodide going to attack on? Least hindered side, right? It's an SN2. Iodide's going to attack on the least hindered side. And that's the methyl. Backside attack. Break carbon-oxygen bond. So we get those are the two products we get if we use one equivalent of hydroiodic acid. If we use a second equivalent, then that means we're going to convert the ethanol to ethyl iodide just like we did right here. So make sure that that's the thought process. This requires a lot of thought process. Here we have attack at least substituted side. I want to say that, and I also want to go back up here and make a little note about watch for carbocation rearrangements. And that's what we're going to do anytime we make a carbocation, especially a secondary one. All right, so in order to cleave an ether which is so stable we could use it as a solvent most of the time, we have to use hydroiodic acid, hydrobromic acid, and we have to heat it up pretty high to do this. If we have an ether that's in a three-membered ring, of course, which we call an epoxide, this reaction happens readily at room temperature. Why would that be? It's a really strained ring, right? It wants to open back up again. Okay, so it's much more reactive. This is 0 degrees centigrade. And let me draw you the two products we get, and then we're going to talk a little bit more about this mechanism. So epoxide mechanisms are going to help you with chapter 10, and epoxide mechanisms are going to help you with a large amount of content in 51C, and that's why I emphasize them. And that's why you're likely to see one of each of the two types we're doing here on this upcoming midterm. All right, so we have this. Oh, and I drew that one wrong. Let me fix that. So we're also going to see some stereochemistry when we're opening up these epoxides. So you will see stereochemistry in these types of problems. And that's going to be really important that you show the right stereochemistry when you're doing reactions with epoxides. So I'll just give you a little warning ahead of time for that. We will be working on problems like this in discussion this week, so really good idea to go to discussion this week and to prepare for the midterm, because everything that's in the discussion worksheet is potential material for this midterm. All right, so let's, these guys, by the way, are enantiomers. All right, so let's see what the mechanism looks like. This is going to be our acid-catalyzed mechanism, which is a mechanism type of a certain type that would be on the midterm. An acid-catalyzed ring opening of an epoxide. Okay? The first step is the same first step that we've been doing every time we have a HBr or HI. We protonate the oxygen. All right, so, and then we do that when we protonate first. That's the fastest reaction that occurs first. Acid-base reactions are extremely fast, and that also has a bonus in that it protonates to make the oxygen a better leaving group. So just like that. And then what happens is the bromide that we just liberated, this is our conjugate base, comes in and does backside attack. Okay, it can attack on either side. Both sides are equally substituted. As we're going to see, when they're not equally substituted, it doesn't attack on both sides. But in this case, it does attack on either side equally. So let's have it attack on the left-hand side. Just like that. And it's backside attack, therefore inversion of configuration. All right, so what's going to happen is, just like we did inversion in chapter 7, we move these groups up a little, but they still stay in the same orientation. And the inversion happens when the nucleophile comes in on the opposite side of the leaving group. That's where we get our inversion. So let's draw the product there. And I usually draw the incoming nucleophile and the oxygen in the plane. It was a little easier to see here. On the right-hand side, we are not attacking the right-hand side. So those groups are going to be in the same spot here. On the left-hand side, we attack the bromides opposite the leaving group. So I'm just moving this hydrogen up a little bit. I'm moving the methyl up a little bit, but they still have the same orientation. So just like that. I'll just use, I didn't leave enough room for CH3, I'll just write ME. ME is a good abbreviation for methyl that you can use. Feel free to use that on the test. All right, so that's one possibility. The other possibility is for the bromide to attack on the right-hand side, so let's try that. So we're going to attack on the right-hand side, kick electrons up onto oxygen. The hydrogen moves up, inversion. The methyl moves up, but they still keep their same orientation. So now, here's what it looks like here. This is the other enantiomer. So we move the hydrogen up a little bit, we move the methyl up, but they're still in the same orientation. On the left-hand side, we keep the groups exactly the same way that they are, because we haven't attacked that carbon. There is no inversion on the left-hand side. So it looks like that. And these guys are a pair of enantiomers. And it turns out that once you protonate an epoxide, it's so reactive that you can attack it even with weak nucleophiles. Bromide's a good nucleophile, but you could attack with water and alcohol, and you will open up easily. So let's look at some examples of that. So strong acid catalysis plus water. So I usually write H3O plus because if I take a strong acid catalyst like sulfuric acid and I put it into water, what does it do? What does a strong acid do? It essentially completely dissociates. So our main thing here is H3O plus. So I often use H3O plus in my mechanisms when we have a strong acid catalyst in water. And this is what it looks like. I'm going to draw you the product and then we will show you the mechanism coming up. I'm going to write plus enantiomer. So basically the way that I handle that, when we have a pair of enantiomers formed, when I first start testing on it, I want you to actually draw the enantiomer. And then after that, you graduate and you can write plus E. But for this first test, if there's a pair of enantiomers formed, I want you to show both of them. Because I want to make sure that everybody knows how to draw a pair of enantiomers, because not everybody in this room knows how to do that. So I want to be able to make sure that you can do that first. Okay, so this reaction here, we're going to go through the mechanisms here. Same mechanism as above. Except that water attacks instead of bromide. And you can also do a strong acid catalyst with an alcohol. And this is what it would look like. We're going to draw plus C, and then again, we're going to eventually, in one way or another, we're going to show the mechanism to both of these, for both of these reactions. Either, and the way we do this is we do it either here or we do it in discussion. So any mechanism that you see here in class or in discussion is possible test material. It's kind of the way I roll here on that sort of thing. So we have this plus enantiomer. And then same mechanism as above, so I'll just do ditto marks, except methanol attacks instead of water. All right, so what does the acid do? The acid catalyzes the reaction because it protonates the epoxide, which makes it a better leaving group, which makes it very easy for nucleophiles to attack and open up the ring. And this is especially important when the nucleophile is a weak nucleophile, such as an alcohol or water. All right, so we said that this was a symmetrical epoxide. We can have attack on either side. Let's see what happens, and you might be surprised about this, if we have an unsymmetrical epoxide. So I didn't bring my laser pointer still in my car, so let's talk about this. Do you see on the left-hand side we have an ethyl and a methyl? It's more substituted on the left-hand side. On the right-hand side we have just a methyl. So let's see what happens here. Okay, so we're going to start off with optically pure single enantiomer. All right, what do we get? Here's our product, and we're going to go through how we get that. Only one product, single product. We do not get a pair of enantiomers here. We do not get the enantiomer. And so I'm going to draw it, and then we're going to, and that's not even the enantiomer, is it? What would we call this product where the bromide attacks on the opposite side? Are they enantiomers? We have actually different connectivity here, so these are not even enantiomers. We call them actually regioisomers. All right, so that means that in one side, and when the first product we attack on the left-hand side and the second product we attack on the right-hand side, we don't get any of the second product. So let's put a big X through that. We don't get any of that. There are what we call two possible regioisomers. But only one is formed. So we call that a regioselective reaction. And it turns out that, what side is the nucleophile attacking on here? Most substituted or least substituted? It's attacking on the most substituted side. Nucleophile only attacks at the most substituted side. That doesn't sound like an SN2 reaction, does it? If it was an SN2, a pure SN2, we did get inversion of configuration, and it was backside attack, but we certainly, if it was an SN2 reaction, we wouldn't get attack on the most substituted side. So something's amiss here. This is not exactly what we would expect. Same goes for other acid-catalyzed epoxide ring reactions. Again, if we start with a single enantiomer, as long as it is unsymmetrical, we only get one regioisomer. So we'd have methanol come in here, and you can see the methanol is just taking the exact place that the bromine takes. Everything else that we draw is going to match the top red drawing exactly, except that now instead of the bromide, we have methanol. So we have only one regioisomer. So the question is, why is that happening? There is an explanation in your book where they talk about the transition states for the two possible regioisomers. And so what I did a couple years ago was I went through the explanation the way the book explains it, and then I went through this explanation, which is an alternative explanation that I'm going to show you. And I took a show of hands to see who liked which explanation better, and most students liked this explanation. It was overwhelming. So I'm doing a different explanation from the book for this. This is not something I will ask you to explain on the test. It's too complicated. But if this doesn't make sense to you, look at the explanation in the book, and if that makes more sense to you, then go with that. It doesn't matter which way you choose. Okay? So here's an explanation that most students find a little bit easier than looking at the structure of the transition states. And so the explanation is, bonding in the protonated epoxide is unsymmetrical with the more highly substituted carbon bearing considerable partial positive charge. The nucleophile attacks this carbon even though it is more highly substituted. That doesn't sound like it's easy to understand at all. So let's go through this. So what I'm going to do is I'm going to take this protonated epoxide. Let's protonate it here. We'll skip that step. And I'm going to draw resonance structures. So now remember the rules for resonance structures. We're going to be doing something a little unusual here. But the rules for resonance structures are atoms stay where they are, you move around electrons. We don't commonly break a sigma bond in a resonance structure, but that's allowed, as long as we are just moving electrons and not atoms. So I'm going to be I'm drawing three. So here's the first resonance structure right here. Okay, after protonation, there's our first resonance structure. And then what we can do is we can go here and we can break this sigma bond. Again, as long, it's weird looking, but as long as we are not moving atoms, we are moving electrons, that's okay. If we do that, we get a tertiary carbocation as a resonance structure. If we move it the other way, so I'll use a different color for that. If we break the bond this way, then that gives us a secondary carbocation. What's better, a tertiary or a secondary? It's a tertiary carbocation is better. And so this one, of course, is the best resonance structure. But this is the second best. They're both very minor, but it's the second best. And if we look at the hybrid, and what I'm going to do is I'm going to draw a hybrid of just the first two resonance structures. I'm going to leave out the second one. I'm going to do just a hybrid of the first two, and then you can kind of see where this is coming from. So here's my hybrid here. So I'm dotting this bond here. So that bond, and it turns out that bond is going to start lengthening in the transition state anyway, because we have very high degree of ring strain. And so if that bond lengthens a little, the one that I have dotted, that's going to relieve some ring strain over on the right-hand side. And so that's going to be happening. Here's my methyl here. And I'm just going to do a hybrid of the first two, so that means I have a partial positive here because I have a positive on oxygen in the first one, none on oxygen in the second, and the carbon on the left has partial positive. And so it turns out that the nucleophile is going to want to come in and attack the side that's the most electron deficient. So the nucleophile attacks the side that is most electron deficient. And that's going to be the left-hand side because that makes a more stable carbocation as a resonance structure. That's the most electrophilic carbon. So that means that this bromide is going to come in, it's going to go here, and we're going to break that bond here. And so that's why we get the only product where the bromide attacks on the most substituted side. So this is kind of a strange mechanism because it's part SN2 in that we get backside attack and inversion of configuration, and it's part SN1 because we are forming some partial positive charge on the carbon that would make the best carbocation, even though we're really not forming a complete carbocation. So it's kind of a mix of SN1 and SN2 is the best way I have to explain it. So mix of SN1 and SN2. So if you're saying to yourself, well, why do we have to go through this big long explanation that's complicated, I don't understand, why can't we just have a regular carbocation form in this reaction? Why do we have to have a partial thing happening? Why can't we do this? So here's the why can't. What if? Why can't we just, that's a much more simple explanation. What if? So if a carbocation forms, then it would look, this is what the mechanism would look like. And let's see why this can't happen. Let's make a carbocation, let's make a full-blown carbocation. Why have something weird bridging something weird thing? Why do we have to do that? Why can't we just make a carbocation? So let's see what that would look like, and then you're going to be able to tell me why we can't do this. That's CH3. ethyl. So we know what a carbocation looks like. If we make a carbocation, then that means that the bromide can come in from either side, right? So the bromide can come in here on the top, and that's the key here. The bromide can come in from the top, and the bromide can come in from the bottom. So what that amounts to is backside and front side attack here, okay? So let's draw the two products that you would get if this is the case. Notice that the bromide is coming in on the same side as the leaving group, the hydroxyl. And if it comes in at the bottom, then we would get this product. Keep going back and forth with methyl ethyl and methyl Me and then CH3. It's totally fine to do that, by the way. Okay. If that happened, we would get two products. Do we get two products? We don't get two products. So that means that can't happen. We don't get any of this. We only get this. And that means the bromide cannot come in and attack on the opposite side there. And why can't it? And the reason it can't, if we look here at this structure right here, the reason it can't come in on that opposite side is that side is blocked by the oxygen because that bond is still intact. Okay, that bond right here is still intact. So the bromide can't come in from this side. It has to come in from the opposite side. So there's our explanation. So if the intermediate was a carbocation, the nucleophile can attack from the top and the bottom, giving a mixture of stereoisomers. The stereochemistry of the product clearly shows the attack of the nucleophile only on the bottom face of the epoxide. The intermediate must therefore be more like a protonated epoxide than a planar carbocation. All right, so this is what I want it to look like. You're going to show the protonation step. If I have this mechanism on the test, you do not need to draw all those resonance structures. You do not need to draw the hybrid. Okay, all you do is you protonate the epoxide and you go like this, boom. So it's a simple two-step mechanism here. We move the ethyl up. We move the methyl up. We still keep the same orientation. And then on the right-hand side, hydrogen stays, methyl stays. So only backside attack is observed. Only backside attack. And therefore, can't be a carbocation intermediate. All right, so here's the thing I just got through saying. I don't expect you to draw the resonance structures. I don't expect you to draw the hybrid. This is a sample test question. You might see this exact test question on your test, or maybe something so similar that you think it's the exact test question. Very high likelihood of that. So that's going to be free points on the test, right? Okay, so let's look at that. So sample question, predict the product for the following reaction and provide a mechanism for its formation. Show all lone pairs, charges, and curvy arrows. Do not combine two steps into one. So let's do this. Now I can write H2SO4 or I can write H3O plus catalytic, doesn't matter. Let's do it with what we have right here. We're going to protonate oxygen first. Arrow comes from the lone pair on oxygen, grabs the hydrogen, we break the hydrogen-oxygen bond. All right. So far, so good. So that means no one's going to miss this problem on the test, right? Because you know exactly, it should look just like I'm doing here. Methanol attacks. Do we deprotonate methanol? No. We don't deprotonate the methanol. Methoxide ion is not going to appear in an acid-catalyzed mechanism. What we are going to do is attack with oxygen on the most substituted side. It's protonated, sorry. Yes. Did not protonate that. Need to do that. Just see, I'm trying to show you what you not do. Gosh. Okay, we're good. I was just going to catch that when I'm drawing the product here. Okay, so that looks like that. We need a positive charge here also, don't we? Positive charge. So boom, this should be OH here. We have our protonated methanol. What's the last step here? What would be the last step here? I'm showing stereochemistry. I'm moving this ethyl up. I'm moving the methyl up, but they still are in the same orientation. Last step is to deprotonate the methanol that just attacked. And I can use other methanol that's in the reaction mixture. This is used as a solvent. Or if you prefer, you can use the conjugate base of sulfuric acid. So both of those would be okay to use as bases to deprotonate. And then usually we only show one product here. CH3, we're good. All right, oh my gosh, we've got 3 minutes here. Let's see what we can do in 3 minutes. Don't worry, this part's easy. Okay, acid-catalyzed mechanism, we got it down, right? This is base-catalyzed or strong nucleophile. Strong nucleophile, right? So easy. This is pure SN2. Oh, that doesn't look like an N. Pure SN2. What happens? Methoxide comes in. What side does it attack on? Least substituted side, pure SN2. Boom. Can you do that? This is something that only happens with epoxides. You cannot do the equivalent reaction with ethers. Not in a million years. Okay, so this is something that only happens with epoxides. This is pure SN2, so it should be very straightforward for you. Here's our methyl here, and we only get one product. So nucleophile attacks on the least substituted side. Nucleophile attacks on least substituted side. If you tried to do the same thing with a regular ether, you would get no reaction. All right, so when we have strong nucleophiles or base catalyzed, the nucleophile it attacks first. We do not protonate the epoxide first. So this is what it looks like here. Let's go through the whole mechanism in the last minute because we're that good. Okay, look at that. Boom. This should be your easiest problem on the test. We're going to attack on the most substituted, least substituted side. We get O minus, then what happens? What do we need to do to finish the reaction? We need to protonate oxygen, don't we? What do we protonate oxygen with? There's no acid present, so don't throw acid in there. What we're going to do is we're going to use methanol. And when we use methanol, you'll see we are actually regenerating our catalyst. So we only need a catalytic amount of methoxide ion. And there it is. Can you do that on a test coming up on Friday? I hope so. That would be amazing. Opposite regioselectivity. We're not going to worry about the alkoxide till Wednesday. And alkoxide is actually a leaving group. We'll explain that on Wednesday, but I do want you to know both of these mechanisms. We'll stop right there and we'll continue this next time.